Hey there, this is a quick look at that group quiz we did today. I think everybody worked hard on it, so everybody gets at least +2 for their participation in this. So it's 18 points plus those two. Sister is pulling a 20-kilogram sibling on a nearly frictionless sled for just a few seconds. We're choosing the best answer, by the way. None of these might be perfect, but there's, I think, a best answer. In this case, this is a classic F equals ma problem. The force is 40 newtons, and we know that it's a 20-kilogram sibling. You want to make sure your units are good. This then will be in meters per second squared. I just simply find A by dividing both sides by 20, and I get 2 is my meters per second acceleration, okay? Meters per second squared. And that's C. Then similar but slightly different, because now we have an electric car that's accelerating, and we know that acceleration. So what is the force that the motor was putting out? Again, F equals ma. That's 1,200 times 15 meters per second squared. That's kilograms. So that is going to be 18,000 newtons. That's not unrealistic for a powerful Tesla engine, say. Okay, you bring a bathroom scale onto an elevator. So this is more of a thought experiment, and you look down and it's reading whatever your weight is. As that elevator goes upwards, it is accelerating you upwards. It needs to accelerate to move you from 0 to some velocity. So you are going to definitely see a resting value when you're standing there, and then a higher value. So really the only two realistic choices, apart from none of the above, but that's not very sensible, I think, in this case, is that it's going to be a higher value and then a resting value again. Well, if it is a higher value than a resting value, that means that it's reached equilibrium and the elevator will never stop. But we definitely know it stops on the second floor. So the moment it stops, it's decelerating, or as it's stopping, it's decelerating. So I think D is definitely the best choice there. I will give partial credit for B. Tossing a ball vertically upwards at the top of its trajectory, the acceleration of the ball is, well, if you go back to that simulation that I asked you guys to do with the cannon shooting a ball or a cannonball, that downward gravity vector never changes. So the acceleration of gravity is always down, okay? Even when it's going up, its vertical velocity is upwards, but its acceleration is always downward. So that's going to be B. A bicycle coasting down. I was thinking downhill. I hope you did too. It's going to accelerate, so we know it's speeding up. Decelerate would be slow down. Maybe there's another way to interpret it. Let me know. I'll check out your quiz. But a bicycle coasting down a long straight road will accelerate. It'll speed up until the force of any resistance, like air, is equal to the force of gravity, and then it'll reach a terminal velocity. Our book did a lot of problems on terminal velocity, so I hope this was in your wheelhouse. But that's the way things work. If you jump out of an airplane, you're a parachuter, you will accelerate until you reach a velocity that is stable, because the wind blowing up in your face as you fall is equal to the gravity pulling down on you. So that would be A. Okay, none of these other ones make sense. A velocity is not meters per second squared. That's the acceleration of gravity. But you're just coasting down a hill. That's not free fall. Anyway, hopefully A was a sensible answer for you. Then finally, a bicycle being pushed over level ground by a force of 500 newtons. It's accelerating because of F equals ma. A bicycle being pushed over level ground with a force will vary based on the value of the mass of the object, based on the mass of the object. A lightweight bike will go faster. A big heavy bike will accelerate more slowly. None of these other ones make sense, but D definitely does. Okay, then on to this one big problem. This is what we call an FRQ in the world of AP physics, a longer problem with parts. an 800-gram rocket, you need to convert that to kilograms. So that is 0.18. You divide by 1,000. That's why that conversion factor is on the board. So the mass is equal to 0.18 kg. We're asked to find the acceleration. We know that that force of acceleration is 12 newtons. So we know F equals ma. So 12 is equal to 0.18 kg times A, so I divide both sides by 0.18, and I get 66.6 meters per second squared is my acceleration for the rocket. Okay, so that's part A. Then part B, sorry if I chopped off the screen, part B says the height of the rocket at the end of the burn. So what's happening is that rocket, the fuel is burning as it goes up, and then it cuts out after 3 seconds, and then the parachute deploys and it comes back down. All right, so for this burn, it's accelerating uniformly at that rate. How far does it go? That's going to be 1/2 AT squared. Okay, we now know the acceleration is 66, and the time is 3 seconds. So it's going to be 33.3 times 9, which if you carry out all those 0.3s is going to be equal to 300 meters per meters, period, is the distance. Okay, so that's what that distance is. The height of the rocket at the end of the burn is 300 meters. Part C then is, what is the velocity of the rocket at the end of the burn? Okay, when things are accelerating uniformly, the velocity is just the acceleration times the time, one of our basic equations. So that's going to be 66.6 times 3 seconds. That's 200 meters per second in this case. All right. Then part D, if the rocket after the parachute deploys has a deceleration of 150 meters per second. So I'm going to interpret this as you did and look at what you did. Some people told me after the quiz that they thought that the rocket goes up and then sometime later on the way down the parachute deploys. I did not anticipate that, because if it's going to decelerate at this high rate due to the parachute and gravity slowing it down, I thought it was that it was clear that the parachute would deploy at the instant at the end of the burn. So sorry if that wasn't clear, but if it was the case, then you'd be saying that this 200 meter per second velocity was decelerated at some unknown amount, but over at the known deceleration, so that's just going to be AT, which in this case is 150 times the time it would take. And then you just divide both sides by 150, and it would tell you how long at that deceleration did it take to knock off that speed. And so that's going to be 1.3 repeating seconds is your time. So that's how long it takes for that parachute to work on the rocket. And then what was the final maximum height? Well, that final height is, again, the distance that it takes to decelerate like that is that 1/2 AT squared equation. In this case, the acceleration is 150, deceleration is 150, and we know that it's 1.3 repeating seconds squared. So when I do that, I think it's worth doing it quickly. 1.33 squared, and then times half of 150 is times 75. And so 132, call it 133, approximately 133 meters, which then you add to 300, and you'd get an answer of approximately 433 meters was your total height. Okay, so that is hopefully at least a few parts that are in your wheelhouse, and we'll see something similar to this in the quiz tomorrow.